Okay, so let us continue. Let us continue. Are you with me?
Yep.
Okay.
Yeah.
Yes, we're
Okay.
here.
Oh, yeah.
All right. So see, so far it's very abstract, right? P of S given X times P of X, P of X given S, P of S. Okay. But let's try to make it a little bit less abstract. Okay. First of all, what is P of S? If, for example, our S was a scalar, if, then P of S is simply a probability distribution on S, right? What you can say that, okay, for example, if you know that your S is around 5, for instance, but you're not very sure, but it's somewhere there, right? Then you can say that the distribution should look something like this. This is 5 here, and this is P of S, okay? So it's a probability. Yes, go ahead.
Sorry, can you start from where we finished at the last
Yeah,
lecture?
yeah, we finished here. We finished here. We finished here, and I was saying that that using setting S, you can introduce different information about your S using this prior distribution. It's called the prior distribution. Okay, this is prior. Okay, and you can introduce your model in this likelihood term. This is called likelihood. It doesn't work. L, okay, of XS. This is likelihood, okay? So I will talk about this. Just hold on. So the goal is to somehow in a soft way to restrict a set of possible solutions, because otherwise there are infinite number of them, okay? Again, if you, for example, dead sure that S is equal 5, it can also be expressed with probability density function. It will just be like this, okay? And it will be equal 1, and it will be delta function like this, okay? That means that you're dead sure about this, and that means that there is no solution, basically. I mean, if you, for example, your equations do not allow for this thing, then, and in this case, it means that you don't need the data. If you're so sure what your S is and why on earth you need the data. Actually, my advisor used to say that in these dipole fitting techniques, because you need to find those R's and data, not so much, but R's locations, and usually optimization is very complicated and it has many local minima, and it is customary to initialize the optimization with some point. So you place dipoles where you want them to be, where you believe they are, based on looking at the data, and then you run optimization. And Richard Leakey says, why do you need all this? I mean, you just use Photoshop to paint it, come on. Well, that's the same story, right? If you know where the source is and what its activity is or which, so it doesn't. Yeah. Now, how? Another point. So this one is this one, and this variance, right? Is your uncertainty, right? About the source, right? About its magnitude, right? It's very important, right? Another thing, how do you encode? Because we are talking not only about amplitude, right? Our goal is to, based on analysis of these amplitudes, find locations, right? Because we look for the entire set of magnitudes, and then we find those that have the largest magnitude and say that that's where my source is, right? Okay, so if you have S, if S is a vector, then I will draw it horizontally, okay, transpose. Then clearly you have S1, S2, and etc. S3, Sn small, Sn big, right? Sn sources, right? Okay, and then clearly, and that's your vector, right? And that probability density function has to be about a vector, right? It's not about the scalar, but it has to be about the whole vector. And if in specifying the a priori information, you can use this spatial information, you can say, for example, the two neighboring sources have very similar amplitudes, for example. Okay, so you can say that if you take the probability density of S1 and S2 is, you know, like S1, some normal distribution, for instance, of the difference between S1 and S2 with some very small sigma variance, right? Means that they're very close to each other, right? And you know, you can do this. You can say that, assume in a very simple case, assume that you only S has only two elements, okay? So you have two locations in the brain, that's it, you know. Then the standard way and the simplest way to give the prior is to use normal distribution idea, you know, just the Gaussian distribution, right? So Gaussian distribution, here I have drawn for you something very similar to Gaussian distribution, right? It would be what? It would be P of S is equal 1 over square root of 2 pi sigma, right? Sigma here, x e minus S minus mean of S squared divided by sigma x squared, right? This is your normal distribution, right? I will draw it. I will rewrite it for the in a proper way. So for the two variables, you already have a distribution that is, let's say, for example, if you're usually we assume here that S1 mean of S1 is equal mean of S2 is equal 0, like mean is 0. But we assume that they have some variance, and this variance is of course non-zero. Therefore, the distribution is usually something like this. These are level lines of this distribution, S1 and S2. And imagine, right? There is something like a Gaussian thing, right, above it. Yeah. And we can say we can for example convey information about how the two sources are connected to each other, how they are communicating, right, through the covariance matrix. Okay, the parametric form of the distribution is this. So determinant of C of covariance, CS, right, multiplied by 2 pi in the power of 1 over 2, because not 1 over 2 over 2 in this case, right? And then exponent minus S, sorry, not this way, sorry, S transpose CS minus 1 S transpose divided by 2. Okay, so this is the parametric form. It believe me, it's exactly this Gaussian thing that is centered around 0 in this case, because we have 0 means, and I didn't fact there are no S minus mean of S here, right? And transpose, only thing that you want transpose is you have to get rid of this, of course. See, but the key here is this covariance matrix, and the covariance matrix is something that determines the shape. You know, for one covariance, if CS is, let's say, 1 0 1 1 0 0, meaning that you have S1 has variance 1, power 1, S2 has power 1, and the correlation coefficient is 0. They are not talking to each other, right? Another covariance could be CS is at 1.5, for instance, 0.51, right? It says that the variance is 1, but they're also dependent, they're kind of talking to each other, okay? You have covariance 0.5 between them, right? And then in this case, for example, your distribution would look like this, right? It will show that there is some dependency between S1 and S2, right? So so basically playing with S with the distribution, you can introduce quite a bit of information about the S itself, right? For example, another example, if you say that you are that S1 much greater in magnitude and variance than S2, then you can say that, okay, this one is 10, this one is 1, and they're not talking to each other, okay? For instance, or they may be talking to each other, it's okay, but, you know, but yeah, but let's forget about it for now. So, okay, so, but this gives you a prior that this source is more active than this source. And when you will be searching your solution for your solution, your solution will tend to have first source more active than the second one, because this is your prior, because otherwise you have a lot of different solutions, and it will try to see how much evidence in the data it can find about this kind of prior, and then modify this prior and give you the result, right? So basically that's the general idea. We typically use normal distribution. Our S is typically very large. Okay, in the simplest case, our S is just, as you know, it's like n sources by one, right? Vector, and it's typically what, like 15,000 by one or something. And we use a prior on this, and to get this minimum norm solution, which is the starting point from everything, we use a very, very dull prior. Our prior in this case, P of S is this 1 over determinant of CS, okay, multiplied by hold on, CS multiplied by 2 pi in n SRC over 2, okay, and multiplied by E S transpose CS minus first CS divided by 2 minus. Okay, so this is your prior on sources. It has covariance matrix CS, and in the simplest case, to get MNE, CS is simply sigma squared identity, where sigma is the variance of the activity of each source. It's all just a diagonal element, and it's just a diagonal matrix, our identity diagonal matrix, yes, which means that we assume that all sources are active with the same magnitude on average. This is not to say, so we have no prior about where we expect our source to be, no, and they're not talking to each other. So it's basically independent sources, statistically independent sources with equal magnitudes. Okay, this is the prior that you have, and this is better than nothing. Okay, at the same time, more elaborated prior, if it turns out it's not true, it's worse than these very non-specific prior. Okay, this is very important. This is philosophically very important. That's actually one of the reasons why beamformers work. Because beamformers don't care about the global picture, they don't care about priors, nothing. And the global solution with Ron priors appears to be worse than the local solution. Okay, with no priors at all. Okay, so.
And why don't we assume, for example, that the sources that are further from the cortex have lower magnitude?
We do assume there is also a modification of this where you can assume this. I will show everything how you can do this. But okay. Yes, there is such a method for sure, and it's very easily obtained by just simply saying that, you know, just having this as a function of depths, right? And yeah. Because MNE actually will tend to activate sources which are on the cortex, very close to the sensors, because their powers have to be small in order to explain the data, right? Because if you have deep sources, then you have to activate them with high amplitude. But because we are looking for minimum norm solution, as you will see, some of the values have to be smallest, the squares of the value. Then it's not very, how to say, profitable for the method to assign activity to the deep sources, because this has to be very high amplitude in order to make to explain the same amplitude data on the sensors, right? And then you choose superficial sources because you can activate them with very little values. And to counteract it, yes, indeed, you scale. You can think of this as scaling the forward model vectors, or you can think of this as scaling CS. That's the same thing, because you will see how it all. Okay, so all right.
I'm sorry, I have a small question about. I thought that in beamformer, in the previous method that we discussed, this assumption was also like Paul Molchanov by default.
Yes, with beamformer it is as well. See, with beamformer there are two things you have to understand, right? The first thing, beamformer also like superficial sources because its magnitude is small, right? And therefore it can make it can make the output small, right? But beamformer has constraints. And it only succumbs to these deep solutions only in case when you have synchronous sources and it can do all this chemistry, right, of subtracting one from another, blah blah blah. Okay. In this case, in the M&E, you have global solution, right? And in the global solution, it explicitly tends to set to put large numbers to not large numbers, tends to activate superficial sources, because then the summation of S sub I squared will be small, right? For I superficial. And yet, because of sum of GI, SI is your data, right? You will have because GIs for deep sources, the norm of these is less than GI for superficial sources. Okay. Then you will for the deep sources, your amplitudes, these have to be large, right? And then some of the squares, this guy, will also be large, because G sub I for the deep sources are very small. And therefore, this thing will have a tendency to, it says that, well, it's better to say that those are superficial sources that are active, because they can be of smaller amplitude. Okay, so it's like if you for example if you go from the depths, let's put this way, if you go from the depths, for instance, right, if you go from the depths upward, okay, so and the norm of the topography will be my answer, because this is from HSC. This second. Слушай, я сейчас не могу, извините, пожалуйста, извините, я сейчас не могу попозже, через пару часов. Okay, so yeah, so and you are moving towards the sense, the surface, right? So and then this is how the magnitude is changing. Okay, the magnitude of your forward model is changing. Okay, the norm. Okay, so the further the source is, the weaker it will be seen, and so the amplitude is smaller. With the same, let's say, if this source is active with 1, you will see on the surface, you will see something like this. And if this source is active as, or if this source, well, you know, let's do it this way. Okay, so if this source is active as 1, then you will see something like this, right? Because this magnitude is bigger, right? The norm. Okay, so and therefore the beamformer, it will be profitable for the beamformer to explain the same data, the same magnitude of data, to assign activity to these sources and not assign activity to deep sources. Okay, just, and how you can counteract it? Well, you can either say, you can say that very simply, you can say that, listen, when you computing this, right, you know what, do this, and alpha has to depend on the depth. So scale the deep sources with smaller coefficient. Don't pay too much attention to them. Okay, they may be higher active, but you just scale them down. Okay, so they will not contribute that much to the actual sum, and then you can balance between these. Okay, so and that's exactly what you can specify in the prior, because your prior is what? C. It's ST CS minus first S, right? If CS is diagonal. If CS is diagonal, this, right? Then this is basically sum of S sub I squared times these diagonal elements, right? CS I, right? I equal 1 to N, right? And those your alphas, okay? So you can specify your diagonal elements to to be certain that for deep sources that you have small, you're expecting larger amplitude because it's CS minus first. See, this is CS minus first. See, it's inverse, right? So you have to say that for deep source, I'm expecting larger amplitude. Therefore, the weights for these deep sources will be greater or less, right? Will be less for the inverse, right? And because it will be less, you will be not punishing in the solution these deep sources, and you will be less biased towards the superficial.
Okay.
Okay.
Thank you.
Yeah. Any more questions, Nastya? No. Okay. Okay. So let's go further. So that was about prior, right? So the prior on sources is again. So the dummiest prior is just identity. So the dummiest prior we will denote it as P of S. We will say that it's a normal distribution with zero mean and with covariance matrix CS. Okay. It's a normal. Just instead of this, right? Instead of this. So this is equal n of 0 CS, okay? It's just normal to say that this is a normal distribution with zero mean because this S doesn't have mean, right? Because if it had mean, it had to be S minus M transpose CS minus first, S minus M, okay? But there is no such M, therefore I assume that it's 0. Therefore you should do it this way, okay? Now this is your, and you have to understand that this is P of S. This is for each, so it's basically big multidimensional distribution. 15,000, whatever. It's huge, right? So and CS is big. CS is 1500 or 15,000 by 15,000. It's a huge matrix. Okay. Now let's see. This was the first term. Okay, or the last term here. But let's here. Yeah, right. This is about this guy. Yeah, about this guy. So now let's talk about this guy. Okay, the P of X given S. Okay, what this is. P of X given S is what? Assume that you know exactly that X is G times S. Just exactly. Just, like, I don't know, S is equal 5. This one is equal 25. And then X will be 125, right? Then if S is 10, then it will be 250. Then how you reflect this is the distribution. Still in a probabilistic manner. Well, you can say that P of X given S is equal delta distribution of X minus GS. Agree? Because what? It's P of X given S, right? So you have G, which is fixed. You have S, and it's 0. See, you delta function. This is a delta function. Delta function is such thing that delta of X it's equal 0. It's equal 1 when X is equal 0, and 0 where X is not equal 0 everywhere else. Okay, it's just delta pulse like this, right? So, and then you go in S равно, let's say G is equal 5, as I said. And your data is 125, okay? So you're going here, going. Then you say that 0, well, what was in the brackets is not 0, therefore probability is 0. You go until S equal 25. You say 25 times 5 is 125 minus 120 minus 125 is 0. So the argument of the delta function is 0. It means the delta function is 1, right? I'm simplifying here a little bit, but yeah, I'm not talking about this infinite delta function, just it will confuse you. So, right? And then 0 is everywhere else, right? Because apparently this cannot be anywhere else non-zero, right? It has to be, right? Now, if you say that, well, it's almost, but not quite, okay? So you have some noise here, okay? You have something which fuzzifies, which somehow, models your uncertainty, okay? So then maybe you can model it this way, right? For that, what? This difference between X and your model has to be the distribution of this noise, right? X minus GS is your noise, because if there is no noise, if it's 0, then it's delta of X, okay? But if it's not noise, if it's not delta of X, if it's some uncertainty, then there has to be some distribution of your noise term. It tells you about the uncertainty. So, and X minus GS is your noise, and noise is, assume it's Gaussian noise, and this is sensors, right? This is sensors. So this is 102. So we will say that noise is also zero mean with some C noise covariance matrix. We can assume that it's white. We can assume we can assume that all sensors are noisy and the magnitude of the noise is the same in all sensors, okay? Or we can record the data without a subject in the scanner, or you just put EEG onto a phantom, okay, and record the EEG and compute, and it will be noise what you will measure, right? And compute the covariance matrix, and that may be your noise prior, no, not prior, no information on noise covariance. Okay, yeah, go ahead.
Yes, I'm sorry. Can you please from the very beginning explain this? We were considering the case with P of S and then Px
Given S.
Yes, from this starting from this, and I understand what is delta function. It's
Okay.
the only thing I understand in this.
Okay. Yes.
Others.
Why do you think there is a delta function here? Because it is 0 here, right? Because it's X minus GS is 0, because you are dead sure what your X is given S. And that's why it's 0, right? And that's why you have 0 extent here, right? 0 extent here. So you're absolutely sure. If you are less sure, then this extent has to increase somehow, right? To model this uncertainty. And if you are less sure, there is some noise here. So it's some variable. So with different S, you get different realizations of this noise. So you don't, I mean, it's a good model. It's like when you have a spring and you have the force, Hooke's law, okay, when you are extending the spring and it generates certain force, right? It's a linear thing, right? It's F is equal alpha delta S, right? But it's not quite, right? You always have something on the difference will not be 0, right? And so there will be some noise here, right? And you can model then this distribution by saying that, okay, the difference between what I observe this and what my model is this is actually some Gaussian random variable with some not very large variance. If your model is bad, then the variance is large. If the model is good, then the variance is small. If you are dead sure the variance is 0, you get delta function. Okay, that's it.
Okay, thank you.
You will see how it all down. Okay, so now see. So basically, we now have P of X given S, which is our forward model again, right? This is our forward model, in fact. Because this one, right? This is our forward model. Because what is X given S? Isn't it what forward models tell us? What are my data if I have sources, right? Well, what are my data? My data are G times S. Okay. Well, how certain I am about it? Well, I mean, there is some noise to it, but we will model it, right? We will at least show that there is some noise to it. So P of X given S is equal to 1 over the norm of covariance matrix of S in the power of n sensors divided by 2 multiplied by 2 pi in the same power. I think I remember. And then exponent X minus GS C noise X minus GS. This is transpose. Okay, divided by 2, I believe. Okay, and minus, of course. Okay, so see, when this guy is maximum, when S is such that
which guy are you talking about?
This guy. P X of X maximum is when S is such that X is equal G times S. X is your data, you have it, you measured it, you already have it, that's it, okay? G is your forward model matrix, you have it, it's all computed. And S is what you are looking for. But clearly, because there are few equations here, you can have infinite number of solutions. And it will be that for infinite number of S, you have this equation that it fulfills. Okay? And therefore, you need some extra equations, some set of extra equations. And those come from the prior that we just spoke about, okay? From the prior on the sources, on the distribution of sources, okay? So then basically hold on. So basically we have S given X multiplied P of X is equal Px given S multiplied P of S, right? Now we need to express, we need to maximize S of X, S given X. We need to find such S that given the data that we measured, we maximize the likelihood. Therefore, we will rewrite this. Okay. And then you say, what do you do with this guy? Well, nothing. You remove it because you have already measured the data. They're already there, this P of X. It's already there. The P of X is there. And the probability of it, if you want, is 1. Because you have already measured it. That's it. I mean, you know, there is no, but if you, for example, have some idea, like, for example, you measured something from one person, you measured something from another person, or you have, for example, some uncertainty from which person you measured it, or I don't know, some other things, you probably can theoretically factor this in here. But if you have X, theoretically, if you measure the data, then you simply ignore it. And we simply write that P of S given X is proportional to this guy, and we simply remove this guy, okay, from consideration, okay, because X is already something which exists, okay. It's no longer random, so you're not measuring it as a random, modeling it as a random variable. It's okay. So, all right, now this is all very beautiful. Now you have to understand one thing, one more thing, that you basically have to find, the task is here, is this: find S such that P of S given X is maximum. Okay, this is our task. This is our optimization problem. Okay, now let's write explicitly what this P of S given X. I will use my notes here, okay, so that I don't make mistake and don't waste your time, okay, on all this, right? Okay, but there are mistakes in the notes as well. Okay, yeah, all right, so okay, so let's write this. Let's write P of S given X is what? 1, let me see, that the P of S given X is equal, yeah, okay, so let's say P of S given X is P of X given S for forward model multiplied by P of S, okay? 1 over 2 pi, I think in the power 1 n over 2, where n number of, hold on, this is not very nice beginning. Let's do this. 1 over 2 pi in the power n sensors, okay, divided by 2, by the magnitude of your noise covariance, okay, determinant, in the power again n sense divided by 2, multiplied by E minus X minus GS transpose Cn minus first X minus GS, okay, divided by 2. All right, so this is this guy, the red one, this one here, right? This whole thing. Okay, now multiplied by P of S. P of S is yet another 1 over 2 pi n, sorry, 2 pi n sources over 2, okay, multiplied by C sources, n sources over 2. We will need only exponents, so, but just for completeness, minus S C S minus first S transpose S divided by 2. Okay, so this is our second guy. Let me this guy is this guy, and yes,
for the second guy, n is number of sources. Yes.
Number of sources. Yes, this is this large guy. This is the first one we spoke about, right? This is the prior. Okay, so and that's our p of, and I have to put the approximate sign, right? Proportional sign, not approximate, proportional sign, because we excluded p of x, right? We just okay. Now, you get this very nicely. Now let's multiply the two. Okay, so if when we multiply the two, we'll get this crocodile over here, right? I will not even expand it. Okay, there is this crocodile made of this and this, right? Of this multiplications, right? We don't care about it because it's we fixed already. We have a fixed covariance matrix of the noise, and we fixed the prior of our data, the covariance matrix of our, not data, of our distribution of sources. But here we have this exponent, and here we have minus, and have x minus gs transpose cn minus 1 x minus gs minus s transpose cs minus first s divided by 2. Agreed? So because when you multiply two exponents, the powers sum, right? So that's because we have minuses, we have two minuses. Okay, now you probably got used to it already, that when we want to optimize this exponential something, we take the logarithm of it, right? Because logarithm is a smooth function, and yeah, so it'll be, if you take the log of this, then you get log of this crocodile, of this guy, right? Plus or minus whatever x minus gs transpose cn minus first x minus gs minus s transpose cs minus first s divided by 2. Okay, okay, right? And you want to maximize it, you want to maximize it, right? Or in other words, you want to minimize x minus g s transpose cn minus first x minus gs plus s transpose cs minus s over 2. Okay, you want to minimize this with respect to s. S is your vector, g is your matrix, x is your data vector, s is your vector, cs is your vector, g is your matrix. Okay, your forward matrix. So nothing. See, I mean, we basically very trivial, right? So we come up with we first set up the distributions, and then we wrote formally so-called this one. This one is called a posteriori probability, a posteriori probability of s given x. Okay, and this is the formulation that we arrived at. Is basically the formulation that allows you to get maximum a posteriori probability estimate of s given x. This is what's so-called MAP, maximum a posteriori probability. Okay, so let's do this. Very simple. You know, this is just a quadratic equation, right? It's quadratic with respect to s. Well, s is a vector, but who cares? Come on, we already dealt with vectors, right? So now I have my my notes here. Okay. Yeah. One other thing, very important. See, let's look closely at this functional. This one is so-called data term because it tells us how much our solution S fits the data through the lens of the model G, okay? And if we are to trust only the data and ignore the forward model, the prior, then we would have, in our case, infinite number of solutions. Just because we have few equations, our data are too little, well, very few data, okay? This guy, second guy, let me choose the color, let's put it blue. This guy, okay, is a prior term, which tells us that, well, in this particular simple case, well, actually, this is not, it may not necessarily be simple, that the data get to come from a normal distribution, that the solution is the sample of the normal distribution with covariance matrix CS, okay? If you trust only the prior, you will arrive at trivial solution will be 0, right? If you ignore the data term, in order to minimize this quadratic sin, S has to be 0, right? So also is not very good, right? So you have like either infinite number of solutions, no, not this way, either 0 or infinite number of solutions. Neither this nor that is good. We need to be somewhere here. This is the sweet spot, right? Somewhere in the middle. And we need to somehow understand what places us here, okay? Okay, what places us here is the balance between how much we trust the data and how much we trust the prior. That's important. An example, real life example. When this kind of approach fails, if you drive in St. Petersburg, okay, for instance, on Kamenostrovsky Lane, okay, it's a lot of buildings, pretty tall, and no satellites can be seen from them, okay? So if you have a tracker like Yandex, whatever, maps or whatever, it shows that you are moving although you are staying. Why? Because it trusts the prior that you are moving at the moment when this smartphone or whatever, the navigation system, lost the data. The data are lost. All it has, just it can rely on the prior. And it extrapolates and says that I'm moving at the speed of, let's say, 60 kilometers per hour every whatever hour, and it's recomputing where I am every time it needs to update. But it ignores the data. The data, if it shows the data, would tell him that no, I'm no longer moving, and it would update the model and would say that V is equal 0, right? But if it doesn't have the data, it has nothing to do but it just uses the prior, okay? So if in our case, if we want to find the distribution of sources corresponding to the data that X that we measured, given the prior, not given, but with the prior on S that we have specified, we need to balance between these two sources of information because both are the sources of information, okay? And how much you trust each other, this guy depends on the noise term. It basically depends on the norm. There is such thing like norm of the covariance matrices. If the noise is small in my data model, then I will trust my data a lot, and I will just only a little bit trust my prior. On the contrary, if there is a lot of noise in the data, I will trust my prior more, and I will tend to have small amplitude sources because this prior is the sources which produce the smallest projection on the CS, right? Basically, this, when you multiply, the smallest this quadratic norm, right? Quadratic form, right, of this guy. So in a simplest case, if you assume, for instance, if you assume that Cn as we not inverse, Cn is sigma noise squared times identity, okay? if your noise, if your noise, as I mentioned already, right? The noise in all sensors is the same, and it's proportional. Its variance is sigma n squared. Okay, and CS is sigma s squared I, and your sources again. The prior is also uniform spatially. All sources are yes, yeah.
Yes, I wanted to confirm this, that prior is just the situation where the assumption that all sensors are active with small magnitude, and
all
sources, sorry, yes,
also.
all sources are active with same magnitude and independent.
Independent of each other. Yes.
So
Yeah.
this is called prior. This is what
Well, any prior, no,
here.
anything is prior, anything prior. But if I specified my covariance like CS here, which I circled now in the then this prior means that this prior, because this prior covariance is this identity matrix. It means that each element is active with the same variance. And since all diagonal elements are zero, therefore it's zero. You know, therefore they're not talking to each other. The covariance is zero.
And in minimum norm estimation, in the method we are discussing, this is the case.
Yes, the classical minimum norm estimation is using exactly this prior. Yes.
Okay.
But in general, maximum a posteriori approach, that Bayesian approach, does not restrict you to using this prior. You can derive many other methods based on, you can specify them, as you said specified. You said that about the depths, right? For example, Anastasia said, I forgot, but yeah, about the depths. Yeah, so you can introduce priors, but here it's a very dull prior, you know, just like this. Okay, so
okay.
So and then if you substitute this into here, okay, and this into here, well, you know, here, all this, right? Then you get C X minus G S transpose 1 over CN squared, right? I multiplied by, let me simplify it a little bit from the very beginning. X minus GS divided by sigma S squared. Agreed? Agreed, right? Yeah, agreed. Right? Because this one is sigma S squared. It's just identity matrix. And yeah, that's it, right? So, and then plus S transpose S, and then 2, of course, here, right? So yeah, plus S transpose S divided by 2 sigma N squared. Okay? Agreed? Because CS is identity, inverse of it is 1 over sigma squared times identity. The only thing which is left is sigma squared, and this norm becomes simply S transpose S, which is simply sum of squares of S, right? All right, and then if you multiply both sides on sigma S squared, okay, because it does sigma S is fixed, right? So you can multiply it and you can say that this is proportional to X minus GS transpose by 2, right? By 2 sigma S, okay? X minus GS plus sigma S squared divided by sigma N squared multiplied by S transpose S, okay? So, right? And then it basically tells you, in this case, it tells you that you have to, you are trusting your prior depending on the signal to noise ratio that is present, that is in your data, okay? This is the signal variance, this is the noise variance, okay? If, right? If I didn't, hold on, sigma S squared, I multiplied, yeah. So but now we have to actually derive the actual solution. Sigma. No, I goofed somewhere. Of course, and you didn't help me, and I goofed badly because it doesn't make sense what I just said. Okay. Hold on. So it has to be sigma, of course, noise here, right? because it's sigma noise squared here, and here it should be S, all right? Because that's a prior about S, and therefore I have an inverse here, right? And then if you do the whole thing, you get sigma noise squared divided by sigma S squared, okay? So basically, let me delete this to make it be more accurate. Sigma noise squared divided by sigma S squared, okay? So basically, it tells you if the noise is large, then trust the prior. Then your S is mainly determined by the prior. If the noise is small, then trust the data, okay? Put less attention to the prior, right? Because sigma noise squared is the variance of your noise, and sigma S squared is the variance of your data. Assuming that sigma variance of your data doesn't change, right? Because it's fixed. You don't know it, but it's fixed. But you have situations with different noises in the sensors, and in cases when the noise is large, then you pretty much, when you minimize this term will not play large role in determining the minimum value, right? Because it's small anyway, and then you will have to trust your the prior. Okay, so anyway, so let's try to minimize. Let's try to do some to derive and minimize it. For this, we go a little bit back to the to this formulation. Okay, to this guy, to this formulation. Okay, so it is x minus gs multiplied by sigma n minus first, this one is transpose, x minus gs plus s c s minus first transpose s, and you can have 1/2, but it really doesn't matter, right? Because 1/2 both in both places, right? So yes, all right. So now we need to find the minimum with respect to s. Take the derivative with respect to s. So it will be Cn minus first x minus gs multiplied by, by G transpose, right? Because this is, you take this as a square, right? You take the derivative of this guy. I also omit the, well, I can put 2, yes, okay. Let's put 1/2 here in the very beginning, 1/2, and then 2 times 1/2, so we don't have too many 1/2s. G transpose, okay? This is the derivative of this guy plus 2 times 1/2 cs minus 1s, okay? This is the derivative. You want to make it 0. Okay, if you are frustrated, don't be, okay? See, think about this as scalars. Just scalars. Forget that these are vectors.
We are taking derivative from
ds of this guy, okay? J of xs, okay, is this. And djxs ds, okay, is this.
Okay.
Okay, I mean, don't be confused that it's matrices. Okay, yes, they are matrices, vectors, matrices, but the correctness of this, or at least sense in this, you can make by assuming that those are scalars. Okay, assume that this is everything is a scalar. Okay, so this is just simply the square x minus gs squared. Okay, because transpose for a scalar is just nothing, right? So it's just a scalar multiplied by some Cn minus 1, okay? So what the derivative of s, this is a complex function, right? Where one function is inside another function, right? You first take the derivative of the larger function, which will be just x minus gs, because it was x minus gs squared, right? 2 times x minus gs. And then for the inner function, what is this? It's g, right? So you multiply you multiplied it by g, right? So the only thing that you of course need to you need to put minus here, right? So because it's minus g minus this guy, right? But if you make minuses and my another minus here, right? So no, it's no minus here. Yeah, this way. Yeah, okay. So now you get rid of this, you get rid of this. Let's see, second. Why? Hold on a second, please. Let me see. CS -1. Oh, yes, minus. Yes, minus. Yeah, you're right. So good. So now, let's expand it. Just very simply, minus G transpose Cn -1 X plus G transpose Cn minus first GS. Agreed? So this one, the first term. Don't forget this minus here. So this minus here, and then minus times minus is plus here, okay? And then plus CS minus first S, okay? So this minus here, okay? Here, of course. So then G Cn -1 X minus is equal minus G transpose Cn minus first G plus CS minus first times S. Agreed? I just simply this thing. Okay, this whole thing. Okay. And that's it, right? Basically, your minus goes, your minus goes. You have to take the inverse of this guy, right? So basically, and multiply it on the left. So you take G transpose Cn minus first G plus CS minus first, okay? Minus first multiplied by G Cn minus first X. So, and this is your S. This is MAP, maximum a posteriori estimate. Okay. So nothing. See, I mean, really, we've written this. What this one? Yeah, we've written this functional that we want to minimize. This guy here. Okay. We've written this. We have taken the derivative of it with respect to S because we want to minimize it, right? We took the derivative a little bit, involving, but not really. Simply quadratic expressions, right? And then your it has to be, let me put a plus here, right? It has to be okay. It has to be right. Okay, yeah, this is equal here, right? And then we are interested in S. So this is equation about S, right? This one is an equation about S. This one. This one is equation about S, right? We know the derivative is equal to 0, right? At the optimum, right? Therefore, there's equation about S, and we simply isolate S. It's like if you have 5S plus 3S is equal 7, for instance, right? You say that 5 plus 3S is equal 7, right? S is equal 5 plus 3 minus first times 7. Okay. The same thing. Right? So this is your S, this is your unknown, this guy, and this one is your unknown. So you take these guys, X, and group these two S here. And then this is
yes, and there is no знак равно here.
Вот равно here равно.
А зачем?
Because I already, yeah, you are right and not right at the same time. Okay, this one is 0. Okay, let's say it is 0. Okay, because the derivative has to be 0. Okay, and from this, it follows that this guy.
Okay. Now I see. Okay.
I'm sorry. Yeah, but yeah.
Thank you.
Okay, and then that's it, right? And then you basically, this is the vector, this is a matrix, you take inverse of this matrix here and multiply this guy from the left, like here, right? This is your story, right? Or just that is, we have S is equal 5 plus 3, 7 S. So you take 5 plus 3 inverse multiplied by 7 is your S. That's what we did here. Okay. So, and then this is your S. This is a vector. Look at this. Now again, we can do the same trick as before, as I was when we were looking at the functional, and we were looking at the role of sigmas here, right? Here. Oops. Here. Okay. So you can take the same thing. You can take Cn, say that it's equal Cn squared I, and Cs is equal Cs squared I matrix, or this is scalar matrix, right? And this is a matrix, of course, identity. Okay, and then you can. I will just simply rewrite it because not to on one hand not to make a mistake, and on the other hand not to. Okay, so and then you can arrive that SMAP is equal to G transpose G plus sigma noise squared divided by sigma S squared multiplied by the identity matrix. Okay. And then this one is G transpose, and Cn will go, and then G transpose X. Okay. And this is your maximum a posteriori solution. This is your minimum norm estimate. Why minimum norm? Because your prior is S transpose identity S transpose, right? So it's exponent of this guy. And that means that in order to maximize this guy, you are looking for a solution which is as close to zero. The sum of squares is equal as small as possible, because this is the sum of squares in the top. So this is exponent in the sum of S sub I squared, right? Minus. And therefore, to make it to maximize this likelihood, you need to make sure that sum of S sub I squared is minimum. Okay, right? Because it's closer to zero, right? And therefore, it's called minimum norm. And S sub I squared is the square of the norm of your vector. Okay, and again, this I that comes here, it's a noise. It's in this case it's I. In more complicated cases, it's actually this I is this I, okay? And the matrix here, sorry, identity here is this identity, okay? You can understand it quite easily because see, G transpose, G is number of sensors by number of sources, okay? G transpose is its transpose, right? And then you can multiply G transpose only by the matrix that is number of sensors by number of sensors, right? Or by number of sensors on the left, and on the right on the same thing, right? So this is the number of sensors by number of sensors. Therefore, here, this I is about noise, about the sensor noise. And this I, because G transpose G is large matrix, as G transpose is number of sources. G transpose has many rows, right? Because G has many columns, right? So, and then you multiply by transpose, this is a huge matrix. And you can add to it only another huge matrix. And this huge matrix is covariance matrix of your prior on the sources, okay? And then this is your I here, okay? So, but you can of course replace them with something more informative. You can measure the noise, for instance, and you can replace the noise data through noise covariance here. You can somehow come up with some prior about your sources and put the prior here. And you can derive from this many interesting methods that that a lot of them already were derived, of course. But yeah, okay. Okay, so let's play with MATLAB so that you can see that this is not so abstract. Okay, so that's the solution, right? So it's pretty trivial. I mean, you know, it's yeah, one important thing. One important thing. This is the data, right? And let's say, of course, everything depends on time, right?
What are you showing? This S map. Okay.
Yes, S of t and S of t, X of t. So for each time slice, we basically apply a matrix of size number of sources by number of sensors. We apply it to X and get the distribution of sources for each time slice. So it's just a single matrix, and this single matrix does not depend on the data. It's not. It doesn't. It depends on the prior. It depends on the noise variance that you, but it doesn't depend on the data. So it's very simple, trivial, linear inverse. I mean, well, basically. And if it's a matrix, each element of this, if each solution, each source estimate, right? This because if you write it this way, see, this is your S hat is equal your W matrix, okay? W, this W matrix, okay? We'll call this W, the whole thing, multiplied by X of t, right? Which is small. Number of this one, this size is this size, right? So and basically each row of this matrix is a spatial filter, if you will, isn't it? It's just a set of coefficients that you multiply with your input channels. Just multiply it with your input and get the solution. So it's not a beamformer, no, because it's an inverse, this set of coefficients does not depend on the data, but it's an inverse solver and it's a spatial filter. It combines the data access with different coefficients and gives you an estimate. That's it. Okay, let's see how it behaves. Let me stop sharing this and let me start sharing this. Okay. Okay, let's go back to MATLAB thing. All right, the same story. Beamforming, we've done it. We've done it. Let's do this. Let's clean everything so that, you know, we don't have any surprises. Of course. What do you mean? Silly thing. Okay. Yeah. Stimulate the data again. Okay, same thing. 0.5 pi. Okay, we're not doing beamformers now. We do minimum norm estimate. Okay. See, I just simply reassigned G3 to G, not to rewrite the code. Okay. So in the expression you saw G transpose, right? We had G transpose, G transpose. So it's here. And also here, let's say you have to understand, here I'm using the slightly different formulation. There are two formulations of minimum norm estimate. They're exactly the same. And just you arrive at one with the way I explained to you and to another, because if you consider a dual optimization problem, but this is more complicated, significantly more complicated. And therefore I'm using here the expression from this dual problem. Okay, so it's slightly different. It doesn't have G transpose G, but it relies on G transpose. Okay, but you know, I sent you a reading about this. It's just simply like I don't know, half a page of derivation, and you will arrive. And simply you can even solve it with matrix identities and show that those that are equivalent. Okay, so but anyway, here is your forward model. You have here is the expression of your inverse operator, WMNE. Okay, so it's G times inverse of this guy multiplied by, just to scale it, and then size of GG1. Okay, so yeah, and then This is just simply the covariance, the noise covariance, which is identity here. Okay. All right. And then let's do the scan, the same thing. But again, we have minimum norm, and we have also triplet of dipoles. And for each dipole, we have its own spatial filter, of course, right? And then we again do the same thing. We do SVD. And take the largest value. Okay, we could have taken trace, won't change much. Okay, now we do the scan. What do you mean? Yeah, we need to compute these covariances because not because we need them to compute the forward model, but because we need them to compute the power. Okay, because we could have, of course, multiplied x and then summed the squares, but R already does it for us. Okay, so that we, right? So yeah, yeah, right. Okay, and then let's plot the scan. All right, here's the scan. Here's the solution. All right, this is not as great as beamformer, right? Because beamformer would give maximum right here in the center. This one has spread out picture, but it's still pretty accurate given how simple it is. And I will try to sell this for you by saying that, okay, what happens if this will be 0.05, for instance? Okay.
By trying to break it and not being able to do it.
Yeah, let's try and break it. Yeah. So now this guy is this. Okay. Well, almost similar. Well, we'll probably use another one, but I'm just not sure we will not break it. But I think we should. Well, actually, we should. Okay. And then do the solution, and then plot the scan. Okay. Yeah, it doesn't break that badly. Okay. Yeah. It's not. Remember how it was with M&E? It plays the source somewhere in the center, and that's it. Yes, but or beamformer. Yeah. Oh, by the way, hold on. No, the beauty thing is not the beauty thing is not about this. The beauty is about this. This is a ratio. Beamformer worked. Yeah, beamformer didn't work even with the ratio. Yes, but this guy will work even without taking the ratio. Look at this. See, I plotted only not neural activity index. See, but I plotted only the based on the post team. Okay, there is no ratio here. See, and this is this last plot, and doesn't really change from the previous one. Okay, so yes, it has some spread out thing, but it pretty accurately localizes the sources. You can be quite sure that it's there, and it didn't depend on the synchrony, and you know, it's a good method. It is a good method. Okay, and if you modify it a little bit, like if you come up with some noise covariance matrix, your sensor noise covariance matrix by recording it in the machine without a human there, you can maybe think about where you want your sources to be. I mean, where you think they may be, like if you studied visual paradigm, for instance, right? You can play with this, and you can get quite a bit from this M&A approach. Okay. Also, we use this when with my colleague from MEG Center, Volodya Kozunov, we had this Gala method, group analysis leads to accuracy, but basically using this M&A principle, this Bayesian inference principles. Well, we come up with a solution that finds the inverse from the group of subject, okay, treating them simultaneously and not one subject at a time, and then average and blah blah blah, and it gets much better solutions, very nice and beautiful pictures, and yeah, so I can maybe, I don't know, show you this. Hold on. There it is. There it was. It's pretty smart. Yeah. The solution. Yeah. Yeah. So I will not talk about details, of course, but that's what you get with M&E, with just simple M&E, when you take each subject separately and blah, blah, blah. And this is what you get with our data. But this is all based anyway on this maximum a posteriori framework. And yeah, so you can see all this ventral pathway of processing visual face stimuli. You see the nice activation in this fusiform gyros. This here, you can see. Yeah, so yeah. Anyway, that's pretty much it, what I wanted to cover. Well, of course, I wanted to cover more. I wanted to talk about statistics. I want to talk about some versions of beamformers, and I want to talk about Lareta, which is a version of MNE, which gives you maximally smooth solutions. There are many things not covered here, but I think you got some flavor of what this whole business is. Understood that things are not as straightforward, and the decisions which method to use are not so clearly cut as you would probably want them to be, and therefore you have to exercise certain how to say intuitions and certain education about each method before you choose it and before you trust it. Okay, because the inverse problem of EEG and MEG is an ill-posed problem. You can put it the way that you have too few equations given the huge number of unknowns. But regardless, it seems to be possible with the power of mathematics and with power of statistics and statistical learning to infer some useful information from this data, yeah, and get some new knowledge about how the brain works. Okay. So questions? No more questions? Okay. You have a chance to ask questions to Dasha. You will have 2 seminars with her, okay? I think. Maybe I will intervene at some, as I promised last time. Maybe I will intervene at some point, and we'll maybe tell you something about maybe statistics or something. But Dasha also should have covered with you some statistical testing. If she didn't, I will ask her to do it on some maybe real data. Maybe without like real mathematics, but at least you will understand how you attach statistics to all this, okay? Because you do need to have statistics always, because you always need to see if the activations you observe are not by chance. Okay, so yeah. And regarding the homeworks, Dasha told me that you asked for extension. I don't know. See, I mean, you had time to do it. I mean, you had two weeks plus to do it. It's not, and you have all the possibility to do the feedback. It's okay. I mean, it's okay for me, but then it makes it difficult to give you another homework, because then you haven't done yet this one, and then it postpones the time Dasha is done with the class and grade and everything. We can, yeah. I mean, I told her you can get the extension, but then we will not go for the second homework. You just play with her in these 2 seminars, and that's it. Yeah. So that's a solution, I think. Solomon's solution. Yeah. Okay.
And
all right.
This home task and the following one will be will sum up in the whole.
Dasha will play. Dasha will play with you with some of these methods. She will show you how to apply it to the real data. And I ask her to tell you about the statistics a little bit. Yeah, maybe, as I said, maybe if my schedule permits, I will also intervene and talk to you a little bit. But now you are in Dasha's hands, because theoretically today should be Dasha's day, but she has some other stuff to do and she couldn't make it to the lecture today. I mean, because there's some other stuff, and therefore, yes, I'm here. But I think it's good because now we finish the theoretical stuff. Okay, you have some time to digest it and ask Dasha questions about it, and she will show you how it operationalizes with them in Python. I tell her to teach you to break the methods in simulations so that you can break them and show. And this is good because if you then play with real data, then you can always say that, okay, let me try and break it. Okay, and then you break it, and then you understand the extent to which what you have found is actually a needle in the haystack or something stable. Okay, yeah, things like this. Okay.
Thank you.
Yeah, thank you. So yeah, email me if you have questions and write your questions in this Google Doc. Yeah, and read the books that are in the class. And we will have we will need to have an exam at some point, but we will, but I wouldn't worry that much about it. You know, it will of course be difficult for you, but it's not. I mean, you are able to use anything you want. It's just I don't care really, and we will grade by curve, in a sense that, you know, if the largest guy who gets the largest score gets A and etc. Okay, well, I'll try to make the exam so that it will not be choosing between 0 and 1, okay, because then there is no resolution then. So yeah, read the books, read this Ilmaniemi book, try to understand, try to rewatch lectures. I know they may be a little chaotic. Well, actually, the explanation itself, I wouldn't say chaotic. My handwriting is horrible. Yes, and it's actually gotten worse with this Samsung thing because it's too smooth. It's very hard to constrain the hand. You know, it's moving too fast, and you know, it's really requires more muscles from the. Yeah, I'm not skilled with this. The other one was the previous one. It was much less smooth, and so a little bit better, not totally better, but a little bit. But still, it's comprehensible if you at least watch it. If you look at the written notes, then it isn't comprehensible. But last time it was like this, by the way. I have it here, so it was much better because it was a difference. So it was this. So it is better. So it's not that horrible, okay? But this one is, yeah. All right. So, and this has nothing to do with Samsung, but it has to do with me. Yeah, yeah.
I think the material was so huge. Okay, I've rewatched several lectures, but I made some notes and I did it at the speed of 0.5 because
Okay.
the usual speed is very high for me, and even doing this, I had difficulties with understanding the homework, and I think that we don't have to. At some point, I'm just like, okay, don't be strict to yourself like this. You don't have to know all of this.
You don't have to know. You don't have to know all of this. You have to, of course, you don't have to know all of this. You have to understand. If you understand about 70% of lectures, it's good.
70.
Okay. Okay. And I suggest you that maybe you know, it's maybe a good exercise, maybe a good preparation for the exam or something, or maybe just a good exercise. Maybe you can have your notes. You mentioned about your notes, and we can go over them, you know, all together. You can maybe share your screen if you don't mind, okay? And we can go over, and I will try, or me or Dasha will try to explain this. So that you say, you said this, you said it, but this one I don't understand at all, you know. And I somehow try to explain why this is, and then it will contribute to understanding maybe, yeah, the whole thing.
Yes, thank you.